Okay, today we're going to talk about universal gravitation. Now we've talked about gravity before. We know the acceleration due to gravity near the surface of Earth is 9.8 meters per second squared. And we know that. And we know force of gravity, which we usually call weight, is equal to the mass of the object times the acceleration due to gravity. And that's about the extent of gravity that we've talked about so far. But remember, this only works near the surface of the Earth. Okay? So if we get far from the surface of the Earth, we can't use this anymore. So let's talk about that for a moment. And we've got, so this is the Earth. You're probably thinking that's a pretty sweet Earth, right? Wrong. Yeah, there's the Earth. Okay, and we know that I'm gonna have to move the Earth. Earth can go over here. Okay, we know that. Hopefully, we know that the moon goes around the Earth on a more or less circular, slightly elliptical path. Okay, and we know that it doesn't crash into the Earth. That's why we know that this acceleration can't be 9.8 meters per second, because it would just go. There is an acceleration, though. Remember, this is just circular motion. Maybe the moon's going this way. So the acceleration is towards the center of the Earth. Now, thinking about this rationally, if we've got this, and then we have a different satellite, maybe this is the DirecTV satellite here, and it's pink for whatever reason. Here, you can see that hopefully it makes sense that the closer you are to the surface of the Earth, I didn't really illustrate that at all, but I'm just going to make an appeal to good sense here. The closer we are to the Earth, the harder gravity is going to pull. I hope that does make sense to you. Obviously, we're not going to be pulled into the sun as hard as, or we're not going to pull as hard on something that's way out here as we are on the moon or on the satellite, and so forth. And that's something that Isaac Newton noticed when he was all thinking about gravity like he did. He noticed that the force on an object, or the force of gravity, is proportional to, and he used this funky looking symbol, like this sort of. You can draw it better. It's kind of like an equal sign had a baby with infinity. But he said that force means proportional to. Probably haven't seen that symbol before. So the force of gravity is proportional to 1 divided by the distance between two objects squared. So the higher the distance gets, let's say the distance is 2, well 2 squared, that means the force is going to be 1/4, or proportional to 1/4. Let's increase the distance to 4. Well, 4 squared is going to be 1/16. So it gets exponentially smaller. The force of gravity gets exponentially smaller the farther away you get from whatever has gravity. And that's what Newton noticed. So what Newton ended up giving us, eventually, is this formula. And this is just the formula for universal gravitation. It says the force of gravity, I could call it Fg, I suppose. The force of gravity equals big G m1 m2 divided by d squared. Notice something here. You've got F equals some stuff, but we've got division by d squared, and that's because Newton knew that that proportion existed, that the bigger the distance, the smaller the force would be. Now, what is G, what is M1 and M2? Well, I'll start with M1 and M2. M1 and M2 are just mass 1 and mass 2. There's just two objects, the Earth and the Moon. The computer screen and your face, anything. Okay, just two objects. And then the distance between them. Okay, now what is G? Well, G is something that we call the gravitational constant. And the gravitational constant is just that. It's a constant. It's true for all cases. And it is equal to approximately 6.67 times 10 to the negative 11. So that is a very small number. That is a decimal point, 11 or 10 zeros, and then 667. All right. And it has a really funny unit because if you think about it, let's talk about that. It's a weird unit because up here we've got force, which is newtons. So if we've got a force, that means this whole side of the equation here has to cancel out to be newtons. Well, all right. So we don't know about G, so I'm gonna leave a space for whatever unit that needs. But we do have mass, which is in kilograms, times another mass, which is in kilograms, divided by a distance, which is in meters. But it's a distance squared, so it's meters squared. So what we end up with, we need newtons equals something kilogram squared meter squared. Well, when we do that, if we want newtons over here, then we're going to need a newton over here, but we're going to need to cancel kilogram squared per meter squared, so the easiest way is going to be meter squared per kilogram squared. So let me write the equation so maybe it'll kind of make sense. You see how if we multiply here, it's going to cancel our kilogram squared, it's going to cancel our meter squared. We're going to be newtons equals newtons, and that's what we want. So it turns out that the gravitational constant is 6.67 times 10 to the negative 11th Newton meters squared per kilograms squared. That's a really funny, ugly unit. But it's just a constant. You never have to, don't try too hard to wrap your mind around what a Newton meter squared per kilogram squared is. That's just something we use. So let's use all this. I'm going to move all this out of the way. So let's just imagine off somewhere in space we have two objects, and they're just in space. Here's object one is a blue box. Maybe it's a blue box. Anyway, object number one is a blue box. And then the second object is maybe a giant orange or a giant yellow circle. Well, we don't really care. Okay, and imagine that the blue box has a certain mass. That's how much would a blue box weigh? Or how much would its mass be? Let's say 1,200 kilograms. And we say that the large yellow circle maybe it has a mass of 1,000 kilograms. And maybe we want to know the force of gravity that one exerts on the other. What's the attractive force due to gravity between these two objects? Well, we just use Newton's law of gravitation. G times m1 times m1 times m2 over d squared. Oh, I didn't give you enough information. We need to know how far apart the objects are. Let's say they're 750 meters. Okay, so let's work this. It's not going to be too hard because we're already solved for f, so that's going to be good. So we'll start plugging in. F equals g, which is that ugly number. I'm just going to leave it as g for now. Oops. That was weird. Sorry, moving on. G times m1 times m2, so 1200 times 1000 over d squared, so over 750 squared. Okay, so you could crunch those numbers, and that really wouldn't be too hard. You just multiply, and you're gonna get g times some quotient. Well, what is it? I guess 1.2 million over 750 squared. I can't do that in my head. Some big number times g, which remember was 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And the calculation's sort of arduous, and I always sort of hated universal gravitation problems just because the numbers were icky and it wasn't much fun, but this really isn't that bad. Okay, it's just plug and chug. Now, maybe if I gave you the force and the distance and the mass of one, you could tell me the mass of the other. If I gave you the masses of both and the force, you could tell me the distances. This formula is not hard to use. You just rearrange it, use your algebra. You know how to do it. And that's that. We could get into a lot more detail with universal gravitation, but we just don't have the time this year. We need to move on to other topics. So that's all I've got for now.